Okay, so it seemed like a lot of people were having issues with the design homework this week, so I wanted to capture a quick recording of how to approach the second problem, essentially reverse engineering the code into a functional block diagram of what the code is trying to do. So to do that, I'm looking back at the code here. And first things first, I'm actually just going to start at the top. So in this, what we've done is we've defined a module. And if we look at it, we say that there's an input. There's at least 4 inputs. So we've got increment, decrement, we've got clock, and reset. On the output, we have a 7-bit bus, which is called hex out 6 down 0. So we have a 7-bit output. If we take a peek inside of the module itself, I'm just going line by line here. If I take a peek inside of the module, what we have is we've instantiated a register, and I've called it value. And then we're basically taking that value and we're assigning it to the output. So I'm actually going to take and move my register over here. How do I know to move it over there? I just saw that the 2 lines of code next to each other. I'm making a register and then assigning a value, assigning it so that it's wired out. The reason I'm doing this is because instead of trying to wire each individual bit, by doing this, I can now further in the code. The trick here is in further pieces of code, I can just implement all the bits at the same time, rather than assigning each wire a value. Next up, I keep going down the lines, and there's a state register. So this is also a register. And it is 2 bits wide. So at a maximum, I see that it's 2 bits. That means I can have up to 4 states. So now we start talking about the actual innards of this thing, what's going on. So always at a positive edge of the clock. So this thing is positive edge triggered from the clock. We got to do something. So if reset, it looks like, so I'm going to draw over here. So we have a reset condition. So this is our initialization or if reset. What we need to do is state needs to be set to 0, 0. Value needs to be set to a specific thing. So to me, I see this and I'm looking through the code here and I don't see it looking like a melee machine. And the reason I see that is because the value is purely given by the state it's in. It's not looking at what the input is. So I know my first state is going to be 0, 0 because that's my reset state. The value that it's providing, which is my output, has to be equal to 1, 0, 0, 0, 0, 0, 0. That's 7 bits. Now what I'm going to do is go into the next statement, the case statement. So we have a reset condition. That's all that line of code did, or those lines of code did. Now we get to see what happens when we go between the states. So I see case state. So whatever state we're in, here's what I want to happen. So if I'm in state 0, 0, given by the code, this is not me because, yes, I wrote the problem, but going purely by the code, in state 0, 0, I assign the value, and then I determine where my next state should go. So it looks like it says if, I'm going to move down here, if our INC, big hint, it stands for increment, if the increment input is a 1, I want to move to state 0, 1. If the decrement is equal to 1, I want it to go to 1, 1. If both of them are 1, or if both of them are 0, I want it to stay in the same state. So let's write that out. Let's literally go line by line. So it looks like it says value assigned. We've got that already captured. I then need state 0, 1. I'm just going to write it over here. My condition to go to state 0, 1 is if increment is equal to 1. There's yet another state. If decrement is equal to 1, it looks like I need to move to another state. Okay. else in every other condition, so increment equals 0, decrement equals 0, so both of them equal to 0, both of them equal to 1, or some other state, I need to stay in the state I'm in. So this is inc and decrement, both equal to 0 or 1. They have to be both the same. Okay, I think that covers what that block of code is doing. Now, the main things you may notice is, well, wait a minute, we don't know what the output is for state 01 or state 11. Okay, well, because, again, this is looking like it's a Moore machine, the state that you're in defines what the output is. So if I keep going down the code here, I see that there's a state 01. Okay, so if I'm in state 01, I need my value to be equal to 1111001. Great. And then if my increment is equal to 1, move to, there's a state we don't know. So I'm going to put it out here, 10. So now that we have, if increment is equal to 1, we're going to move down here. If decrement is equal to 1, it looks like I need to go back to state 00. So I'm in 01. If decrement is equal to 1, I need to go back to that state. And then we end up with the same condition we did before. If they're the same, if increment equals decrement, I'll write it like that. Stay in the same state. Okay. Covered all the code. Let's move to the next one. Okay, if I'm in state 10, my output value needs to be 0100100. If increment, move to 11. Okay, so we got this little circle going. If decrement, move back to state 01. And then same statement. If increment is equal to decrement. And again, what am I saying with increment equal to decrement? If you look at how this code runs, if increment and decrement are 0, it will come to the bottom. Technically, I believe in this code actually, if increment equals 1, it will just increment. It won't actually stop, but that's a fringe case. We'll deal with that later. That may mean we need extra code in here to say if they're both equal to 1. Okay. What we want to do from here is, it looks like we're pretty good there. And then finally, we define what happens in state 11. So the value is equal to 0110000. If increment is equal to 1, we move to 00. If decrement's equal to 1, we go back to state 10, and under those, increment equals decrement equals 0, stay in the same state. And actually, that's the end of the code. There's a test bench down there, but other than that, this is the state machine we defined. So I just transcoded that from the code here. I just looked at each state, each case, looked at what it was trying to do, and we were able to get the information here. So what is this thing actually trying to do? So let's run through it real fast. So that's where the test bench kicks in. So with the test bench, I say, okay, let's start at 00. So let's say we're at 00. Let's say I then throw increment. So let's say I turn increment equal to 1, right? Next, we'll go to 01, and the value changes. And if I keep increment equal to 1, it looks like I move through these states in a circle. And then if I turn decrement on, so decrement equal 1, I go through them backwards. So, okay, it looks like it's running in a circle. And it looks like with the way the code was written, at any point in any of these states, we can reverse or we can change the direction we're moving in. Okay. And then if we ever hit reset, it goes back to 0. what do we need to do from here to figure out what's going on? So let's look at that value for a second. Now in the problem, I try to hint at it, I should have been more clear, is that you are outputting this thing through you're outputting it through a 7-segment display. The big hint there was the hex out. I should have been way more clear. I apologize for that. So with the hex out, basically what's happening is in state 00, if I know that we're using the displays on the FPGA, they have inverted logic. So 00 was 100, 0000. With inverted logic, that means this is bit 0, this is bit 1, all the way up to bit 6. From a logic standpoint, or from a segment standpoint, there's A, B, and we go up to F. A, B, C, D, E, F. My bad. G. So on our 7-segment display, this turns into a 0. 0, 1. Maybe you can figure out the pattern from here. Is 1, 1, 1, 1, 0, 0, 0. Hello? Did my pen just die? I think my pen just died. Nope. Alright, so that would be this. This would probably be 0, 0, 1, 0, 0, 1, 0, which would give you a 2. And 3 would give you 0, 0, 0, 0, 1, 1, 0. Now again, that's also stuff that we got from the code, but the idea here is that it's actually counting up from 0 to 3 or counting down. So the challenge in the problem, if you got that far, is rewriting the code but using output encoding. So now what that means is the state that you're in, you know, these states, let me make a copy of it. I mean, quick drawing of the state table. We're not changing how the states interact with one another. We're keeping this increment and decrement thing going on. That's not what we're doing, is changing that. Instead of labeling this as, say, state 00, I'm going to put an A, a B, a C, and a D just for shorthand here. So instead of A, B, C, and D being like 0001, output encoding says, as long as you have unique outputs for each state, let the state be represented by the output. So for example, for A, it was 1 and then all zeros. So let A, the state itself, be labeled as 100, 0000. That's it. For B, we needed to output a 1, so that would be 1111, 001, and so on and so forth. I'm going to leave that for you to fill in. The idea here was to look at what would happen if you use output encoding. Is there something better that happens? Something more difficult? Does any of the logic effort go away? So that's what you have to explore here. So it's the same interaction. We're not changing any of these arrows, any of the states. We're just changing how we store the state's value in the state register. So I'll tell you one of the disadvantages right now. Previously, if I wanted to store my states, I had 4 of them. I needed a 2-bit register. Now, I need 7. So my register's bigger. But there's a catch. Something else will become probably a lot easier. So I'll leave you up to that to figure out.